To finish the predicting the design of vegetation, the brief summary is that we've looked at the roots, meaning one root. We are very modest here. We do the simplest first, so the simplest analysis empowered us to predict a carrot-like root, meaning a conical root. And the water flow rate pumped upward through that structure turned out to be varying as the volume of that carrot to power 1/3, which means as the length scale to power 1. So bigger diameter at the top of the, meaning at the ground level, means bigger water flow rate into the trunk. And on the trunk, we also dealt with that. We dealt with the trunk with its canopy. This, again, simplest analysis, where the audacity to throw, anyway, the simplest objects, which are spheres at people, led to even more important ahas, namely that the trunk is roughly conical, regardless of the diversity of, I'm talking about conical as an object, or triangular if you want in the profile, regardless of the, in fact, let me sketch it. So here's the trunk. Not exactly that, but looking like that. And regardless of the diversity of shapes of the canopy. So conical with diversity of canopies. This is a big discovery, which is that you start simple, you arrive at a simple feature that supports or depends on a multitude of let's call them features that then make the existing designs appear diverse. But inside of them, there is the pillar, or if you want the main elevator in the building that connects the floors. You see, and the floors, according to the architect, could be arranged into a beautiful body called building, or into an ugly body called a very modern building. You see that? Okay. Now, let's call it the lesson that connects all these things. If you look at the way what we invoked on the way to this level in my resume, is the idea that vegetation is let's call them protuberances rising from the flat ground. They rise naturally with purpose, so that the ground itself puts the water where it came from, which means back into the dry wind. This sort of, let's call it activity, which happens naturally, happens every day in your profession if you decide to continue in engineering, in the design of fluid flow structures for heat transfer. The armies of let's call them thermal engineers are they're like the U.S. Army and U.S. Navy. Okay, they are of two kinds. One Army Corps is enhancing the transfer of heat. How? By making the surface that transfers the heat to the cold wind, or in this case a cold fluid, that surface is endowed with fins. And over the years, these fins have becoming more complicated. They, not surprisingly, these days they are dendritic. They have all sorts of cool features added to them, just like the bulbs on the Christmas tree these days. But the attitude that happens from the mind in engineering has been happening forever, meaning from before the so-called animate, in these forms of vegetation. So that's this part of heat transfer is called heat transfer augmentation. And just like in the military, this Army Corps is not at war with its partner, which is pursuing the exact opposite, which is called thermal insulation. So here's insulation. I gave you the natural example of insulation, which is the hair on the back of the animal or on top of somebody's head. But insulation in engineering is just like heat transfer enhancement, a very thick body of literature with a huge number of drawings and materials stuck, obviously, or separating the hot from the cold. So activities that appear contradictory, but they appear naturally, either out there in the forest or on the backs of animals. In this case, in enterprise, meaning in our living space, those contradictory things are in fact happening hand in hand with the same purpose. All right, where am I? Now, I will start from this little review in the direction of more complicated things. First, I did not say last time that one of the punchlines of the treatment of the canopy supported by the trunk, if you, I hope you read the text, because that's a little bit more complicated mathematically than I can put on the blackboard because of the brevity of time. One of the statements that comes from this piece of analysis is that the transversal dimension, called the diameter of the canopy, should be proportional to the, as an order of magnitude sense, to the transversal dimension of the trunk. And this constant, or let's call it roughly constant, is in equation 10.117. This sort of idea is worth keeping because it allows us to look, let's say, more aggressively inside the canopy and ask, what is the canopy made of? The canopy is made of branches. So here is the, I want to copy my own art. So, well, to rhyme with this conclusion, I make a canopy that's roughly conical. Here's the ground. Of course, the trunk is narrow, and one of the branches has its own trunk-like stem and its own its own, let's call it the personal canopy. This canopy of the branch is usually oriented horizontally, but it is this way. It is narrow at the tip and closer and fatter closer to the trunk. You see, so you can imagine the entire volume of the canopy being filled with these, children. And another thing, one such extension belongs to a particular chunk of the trunk. That chunk in this model is called of height x, and actually it's not x but h of x, and x is the dimension measured from the top. Okay. There's a reason why all these x systems of coordinates start from the so-called top. The top is the sharp point, and if that is the way you construct your mathematics, then you can explore this great idea of postulating, meaning assuming, based on a technique, that things that vary, meaning are not of constant thickness or constant speed or constant some other thing, vary according to formulas that are power laws, such as y equals constant times x to some power, and then the exponent on x becomes the unknown. All right, and this is what's done in the book. The length of the branch is called the length of it is called the length LB. The diameter of the branch itself is called DTB. And then the diameter of the canopy of the branch is called DCB. So this is a new notation, which is the start of the part of the analysis that that is in the book, but I skip. I skip because I have other things to show you. Several moves are made along the way. One is that the analysis mimics what we did in the last lecture for this simple look at the trunk with the canopy. We call the ratio of meaning the aspect ratio of this particular drawing, see, dTB of the branch divided by the length of the branch, a factor called B, and then the same ratio for the canopy, DC branch divided by the length of the branch, another factor called A, where the A and the B are the same ideas as in the previous lecture for the treatment of that picture. And then for you to know what to look at before all of us move forward is that I'm skipping. In fact, I'll put the ... equations 10.119 to 10.129. And now the end result, after you go through this, is that the water mass flow rate that so now we're looking at the tree with all these things installed on it is equal to I had this formula on the board in the previous lecture, the density of water and then the speed of water seeping forward, upward through the top of the root, and then pi over 4, and then the trunk diameter at ground level. And then the book shows, if you use these subsequent results, it is essentially a similar proportionality. I skipped the constants. There's a fat group of constants. And then the canopy diameter at ground level. All right. So if you look up from above, this water pump called the tree is putting into the air a flow rate of water proportional to the length scale of the disk that represents the canopy projected on the ground level. So if you look from above, you'll see this as the canopy, and this sort of dimension is proportional to the mass flow rate. I already previewed the aha, which is that big trees put more water into the air. Small little plants put a lot less per plant. Next comes the fruit of this journey, meaning what we find deep into the cave. The thread of solid gold, which is, well, look. So according to the Constructal law, if I am allowed to make fun of myself, according to the Constructal law, by the way, here's something that's a very serious joke. Since I wrote this Constructal law in 1996, and I wrote it several times, no one has refuted it, okay? So then Adrian, about 3 years ago, decided to refute it himself, because I questioned myself. And if there's time, Jacob is supposed to make a list of things to remind me. I'll tell you what I picked as an obvious example that violates. In fact, I'll tell you. If you look, say, during a downpour, torrential rain, streets covered by gravel develop not straight rivulets of rainwater, but rivulets that alternate little pools of water and then flow over the dam. They're called cataracts. Yes, cataracts. That's why in the eye the vision deteriorates, because the rays of light are impeded by small things that float in the eyeball. All right, so I said, this is an obvious. First of all, it's happening naturally, all sorts of scales. If the flow is big, like in a mountain valley, then you see these things happening large scale. And guess what I discovered? Yeah, that to flow on the ground as a sequence of pools and free fall, pool and free fall, is faster than to flow down a smooth incline. Wow. Meaning I was happy to be proven wrong. Wrong to question what I thought deserved to be questioned. And that was just, yeah, it's kind of, you still do not believe what I tell you. Go check it yourself.